Okay. So, good morning. First, since I have the microphone, I want to also take the opportunity to thank Peter for everything he's done for me, and to the organizers for the honor of contributing to the conference this way. Our first speaker of today is Werner Muller from the University of Bonn, and he will discuss the asymptotics of automorphic spectra and the trace formula.
Yeah, I'm very happy and pleased to speak on this conference in honor of Peter. And I thank the organizers very much for inviting me to give this talk. So I know Peter since quite some time. I think it's now 25 years ago when we met the first time in Stanford, and he was working with Ralph Phillips on spectral problems and other things. And over the years, I met him, well, on various occasions in Princeton, on conferences, and I always enjoyed talking to him, and conversation with him is very inspiring. So I got many interesting suggestions and so on, and this is also related to the current talk. But I also want to add some additional remark. So last night we heard that Peter is also concerned very much about the well-being of other people. And I experienced this myself during my visit in Stanford. Namely, he cared about entertaining me. And he got one of his PhD students, Rolf Landelius, who is now in the money market, and to introduce me to nightlife in the Stanford area, which I enjoyed very much. And later on, he introduced me also to nightlife in Princeton, which essentially means to visit the Triumph Brewing Company. Anyway, so, well, the subject I'm going to talk about is about spectral theory of automorphic forms. This is a subject which goes back to Mars and Selberg, who introduced spectral theory and the theory of automorphic forms. And, well, this subject is also related in many ways to Peter's work. And so it started, as I said, with the introduction, in particular with the work of Mars, who introduced non-holomorphic, the concept of mass forms, non-holomorphic automorphic forms, and Selberg, who introduced the Selberg trace formula, I think, with the purpose to study spectral problems. Well, so in this setup, we consider a hyperbolic surface and the Laplace operator, the hyperbolic Laplace operator acting on a surface. And then a mass form is a smooth function, which is an eigenfunction of the Laplace operator and satisfies some growth condition at infinity. So examples, the basic example is a square integrable eigenfunction and the non-analytic Eisenstein series. And, well, Mars also extended the Hecke theory, so introduced L functions and anything like this. But now what means spectral theory? Well, spectral theory, as we see it today, means that we regard the Laplace operator as an operator in L2, unbounded operator, and then it turns out it's essentially self-adjoint, and so we try to understand the spectrum of this operator. So this is, well, the eigenvalues, so it has a discrete spectrum, and this is, for example, what we would call the discrete automorphic spectrum in this case, or what I call it. And, well, the study of the spectrum, there are many problems related to the study of the spectrum. So you wish to understand, for example, well, it's not so clear if there exist any mass forms. And this is related the Weil law, and it's also related to the famous Phillips-Sarnak conjecture, which says that cusp forms, mass cusp forms, are essentially related to the arithmeticity of the underlying group, and you expect that for generic groups in the moduli space, there will be no cusp forms at all. So in particular, there will be no eigenvalues bigger or equal to 1/4. Well, another very famous problem is the Selberg conjecture about the eigenvalue, which states that for the congruence, principal congruence subgroup, the first positive eigenvalue is bigger or equal to 1/4. There has been a lot of work to establish this. So first Selberg proved the 316 bound, and then Peter has been involved in improving this in various papers, and as far as I know, the latest estimate is this one, 0.238. But today we will hear about this in the talk of Frieden Shahidi. And then the other problems which you want to study, Asymptotic conjecture about distribution of Hecke eigenvalues, statistical properties of the series of L functions, and quantum ergodicity, everything, all things which are related or also initiated by Peter. Well, the main difficulty in studying these problems is we are mainly interested in congruence subgroups or arithmetic groups, and in this case, the corresponding surface is non-compact, which implies that the Laplace operator has a large continuous spectrum, and this makes it very difficult to study eigenvalues because from general principles in mathematical physics, we know that embedded eigenvalues are highly unstable. And the basic tool is Selberg's trace formula. Well, I think it was introduced by Selberg exactly for this purpose, to study the existence of cusp forms. In this case, later on, Arza, as we know, Arza extended it to general reductive groups, but in this case, the purpose was to compare the automorphic forms on different groups. But now it turns out that it, again, seems to be very useful, now the general trace formula due to Arza, to study spectral problems on higher rank groups and spaces. Well, now this is how everything started with, but the modern approach is, theory of automorphic forms over the years has evolved in quite substantially, and the current framework which we are using is the adelic framework. So this means we consider now any reductive algebraic group over the rationals, and then the ring of adels and the adelic group. So everything is now put in the context of representation theory. We fix a character on the center, unitary character, and then we consider this space L2 functions which transforms according to this character under the center, and which are square integrable. And then the group, the adelic group, acts on this space through the right regular representation. And then the theory of general theory of Eisenstein series of Langlands gives rise to decomposition. In principle, it gives the spectral decomposition of the space. So first of all, it decomposes in a discrete part and the continuous part. The continuous part is described in terms of Eisenstein series, and the discrete subspace is the largest subspace which decomposes discretely under the representation. And so, and there's another important subspace, the space of cusp forms, which is singled out also. Oh, sorry. so which is singled out by this condition. These integrals should vanish, so you take a proper parabolic subgroup, unipotent radical, and then all these integrals should vanish. This is the space of cusp forms, and it's contained, it decomposes discretely, and so it's contained in the space of L2 representations. So we introduce the space of cuspidal representation, square integrable representation, and there's also the notion of automorphic forms in general, which in some non-precise way could be defined as the representations that occur in the spectral resolution. But this is not the right definition because it's not uniquely defined in general. And then related to this, it's a series of automorphic L functions. First of all, there's the Langlands dual group, which is a semi-direct product of a complex reductive group and the Galois group. And then if we have any automorphic representation, which is it's a product of local representations, and then if the local representation is unramified, there is a unique conjugacy class associated to it in the Langlands group. And there's a finite number of places outside of which the representations are unramified. And then if you pick any representation of the Langlands dual group, then associated to this, we get this partial L function. Converges in some half plane. And then one of the main conjectures of Langlands is that all these L functions emit meromorphic extensions and satisfy a functional equation. And special cases can be treated, namely L functions that occur in the constant terms of Eisenstein series. This is the Langlands-Shahidi method. And here are two basic examples, namely the standard L functions. In this case, the underlying group is GLN, and we have the standard L functions associated to the standard representations and the ranking Selberg L functions, which are the unramified places are defined in this way. Well, there is and now Peter introduced the concept of families, to study L functions. Well, one of the main interests of Peter is to study zeros or statistical properties of zeros of L functions. And one of the main facts of this theory or Langlands conjectures there is that everything can be reduced to the standard L functions. And well, so you wish to study the zeros of the standard L function statistical properties, and then one comes up with the fact that there are different kinds of automorphic forms which arise in different ways associated to Galois representations or mass forms and so on. And so this, and in order to take care of this, it's necessary to study automorphic forms in families. So family is a certain subset of the universal family cut out by certain constraints like fixing the central character or considering self-dual forms and so on. And one of the basic issues in studying families is that you want to understand cardinalities. So first of all, we have to introduce the conductor. Well, there's the conductor which describes, so to speak, ramification, and then it's extended by, well, in principle, a number which comes from the infinitesimal character. So this is then, it's completed by some function at infinity. This is the analytic conductor, and you order automorphic forms by the analytic conductor. And so there's the basic result of Bromley, which says if you consider cusp forms where the analytic conductor is less than x, then this is a finite set. So it makes sense. So if we have now any family and we consider the subset with conductor less than x, then it's a question, does this, or it's one of the basic or first problems which you want to answer in this context is, does the cardinality of this set have some asymptotic behavior? Well, according to what Peter, I think, thinks that it should have an asymptotic behavior, should behave like a power of x. And a more precise conjecture is, so if you consider the corresponding standard L function and the coefficients in the Dirichlet series, then a more precise statement is if you sum up the corresponding coefficients of the L series, then conjectural, the asymptotic behavior should be given by this. There is some constant depending on the representation. This is certainly, there should be no pi, I think. Or, yeah, depending on pi, and then appears the cardinality of this set of the family. Okay, so these are the first question which you want to answer in this context, and so and this is related to the two questions which I want to discuss in this lecture. So the first question, this is more or less related to the so-called while law. So to begin with, let me recall what while law actually is. So we start with a so while law, I mean, as it indicates, has been studied first by Weil, and then we consider, yeah, in the case of three-dimensional domains. And in more general context, we consider a compact Riemannian manifold, the Laplace operator, and its spectrum, the eigenvalues. And then the interest is so in the counting function of the eigenvalues, and the theorem is the general theorem, which is due to Avar-Kumovic and Hermander in a more general context, says that the counting function has a leading term given essentially by the volume, and the remainder term is of lower order. Well, a weak version of this formula is, so where you don't have any good estimate of the remainder term, it's just little o of this. And well, let me briefly say a few words about the methods, how you prove this. One of the methods is the heat equation method, which of course Peter doesn't like very much, but anyway. It's to illustrate how it works. It's the best way to look at this. So you consider the heat operator, and on a compact manifold, it's trace class, and then you have a kind of elementary trace formula, which says the trace of the heat operator is given. You take the kernel, so the heat operator has a smooth kernel, as an integral operator with a smooth kernel. You take the kernel, restrict it to the diagonal, and integrate over x. And then standard methods how to construct this kernel in an approximate way gives rise to such an asymptotic expansion if d goes to 0. And then you apply a standard Tauberian theorem. Well, this gives you only a weak version of the Weil law. Well, if you want to have an estimation of the remainder term, then you have to use a more powerful method. This is the wave equation method, which means instead of the heat operator, you study the wave operator and its singularities. Well, in the context of a hyperbolic surface, this can be made much more precise. So if you consider now a compact hyperbolic surface, then, well, the heat this is essentially taken care of by the direct trace formula, which in the case of a compact hyperbolic surface is this formula. So we have to make it simply, we have to somehow replace eigenvalues by the square roots of the eigenvalue minus 1/4. And then there's this term containing the area and an infinite sum. Each closed geodesic makes a contribution through its length. So the key application is now how you use this formula is that you're able, so in principle, one would like to insert in a trace formula the characteristic function. So you want to count eigenvalues in a fixed interval. Well, unfortunately, we cannot insert the characteristic function, but we can make up a test function which essentially is concentrated near the interval, and then we shift the whole thing. So this is the key application of the trace formula. So you're able to estimate eigenvalues in some interval. And now in the non-compact case, well, we are first facing the problem that the operators which we want to consider, neither the heat operator nor the wave operator, I mean, the wave operator has no trace in the true sense, but it gives rise to the integral operators and is not trace class. So one has to deal with the continuous spectrum, and the continuous spectrum is described by the Eisenstein series. And then, so every cusp has an associated Eisenstein series. You take any of these Eisenstein series, expand it in another cusp in a Fourier series, and consider the constant term, the constant Fourier coefficient. So the constant Fourier coefficient has this form, and you take this matrix, this is the scattering matrix or intertwining operator, and then a much more complicated formula, trace formula looks then, this is the trace formula for a non-compact surface. The main contribution of the continuous spectrum is this integral involving the logarithmic derivative of the determinant of the scattering matrix. And this is now you have to struggle with. Well, to see what the problem is, it's a good idea to return to the heat operator. So if you insert, well, the trace formula as stated works only for functions which are the Fourier transform of a compactly supported function, but it can be also extended to more general function, rapidly decreasing function. So in particular, you can insert the heat operator, and then most of the terms are easy to handle, and you end up with this formula in T. And now you see, if you want to get out any information about eigenvalues, so you let T go to 0, and you want to know if this series is diverging or goes to infinity. Well, this can be only, so the formula allows you only to understand the behavior of the counting function and the winding number getting out of this, of the logarithmic derivative. So the main problem is to understand the behavior of this logarithmic derivative or of the scattering matrix. And for arithmetic groups, this can be done. Namely, they can be expressed, for example, for the principal congruence group, it's due to Huxley. It can be expressed in terms of known functions from analytic number theory, namely the Dirichlet L functions. In particular, for the modular group, we have this formula expressing the scattering matrix in terms of the Riemann zeta function, and then using standard facts about behavior of the logarithmic derivative or of the derivative of the Riemann zeta function and L functions, you get this estimate. And this is enough to conclude that in this case, for arithmetic groups, we have the Weil law. Well, by this method, you get only a weak version of the Weil law, But now if you use the full power of the trace formula, you get also estimation of the remainder term and so on. Now let's consider the general case. Well, in the general case, we consider now, as before, maybe a semi-simple group, the real points, and the maximal compact subgroup, and the associated Riemannian symmetric space, and an arithmetic subgroup, say a congruence subgroup, and the associated locally symmetric space. Well, then we have, also, let me move this. So then we can talk about the space of cusp forms. Now we are in a real setting, but everything is defined in exactly the same way. So using the theory of Eisenstein series, we can single out, we get the spectral solution, and in particular, we can talk about the discrete subspace, which decomposes discretely in irreducible representations of G of R. And, well, so we have discrete subspace decomposes in the cuspidal and the residual spectrum, and we can consider the corresponding counting function. And the first result in this context is due to Donnelly, who shows that at least the eigenvalues cannot grow, or the eigenvalue counting function cannot grow any with any higher power as the one predicted by the Weil law. So of course, it doesn't say anything about existing of cusp forms because it can be zero. So then the residual counting function, this is still a problem. So there is an estimate, it also grows at most polynomially, but what you would like to have is that it grows with lower order than the cusp forms. Well, this is known in the case of GLN, but in general it's still, I think, open. And now, as far as the weak version of the Weil law is concerned, in this context, we have the result of Lindenstrauss and Venkatesh, who proves for G split and of the adjoint type, they prove the weak Weil law, or the Weil law in this sense. Well, the interesting thing is that they're not using the trace formula, but they use Hecke operators, which are also, of course, only exist for arithmetic groups. This is a very interesting approach, and it's certainly interesting to see if this gives if it has other applications to study the spectrum. So there are previous results. First of all, Steve Miller considered the SL3 case and the full group SL3C, and he proved the Weil law in this case, and I myself considered SLNR, the SLN case. Well, this is only the Weil law for the spherical case, so you consider only the Laplace operator on spherical, on functions. But you can also confix any K-type and consider, so to speak, the forms which contain this K-type. And then there's a more general result, which I proved. So you fix now, well, G is GLN. And now if we fix any, also, again, this problem. Oh, let's see. Yeah. So this is now a formula which works for any K-type, and the K-type appears essentially appears through the dimension of the corresponding representation. So now this is only without any estimation of the remainder term. And the next thing is, one of course would like to understand how to estimate the remainder term, and this is what Aris Labid and I did some time ago. So in this case, so far it works only for GLN, and so we consider as usually A, the Lie algebra of A and the Cartan decomposition and so on, and the Plancherel measure, and then the theorem is a more sophisticated statement, namely, we're not only considering the eigenvalues, but we consider Well, now we have, so to speak, we consider the distribution of the infinitesimal characters. So we consider any subset, open subset, with some nice properties in A star, and then we count cuspidal representations whose infinitesimal character is contained in, if you scale this set by t, if it's so we have any set like this, and then we scale it by t and count the representations with infinitesimal character contained in the set. So we get a while law in this sense and with an estimation of the remainder term. And now if you restrict to the ball, unit ball in A, then as a corollary, it gives you a while law with remainder term in the usual way, in the usual sense. Okay. Well, it's about congruent subgroups, and we assume that n is bigger or equal to 3, so this rules out torsion. And, well, there's also some recent work about self-dual representations. Self-dual representation form a family, and you want to see if the conjectured behavior by Peter is true in this case. So now you count self-dual cuspidal representation, and in a recent series thesis of Kala, he wasn't able to prove an asymptotic formula, but at least he can estimate get bounds from below and above, and with the power which is exactly what you would expect. And well, if you restrict, first of all, if n is even and you consider the full modular group or the full, the maximal compact subgroup, then in this case, he is able to get an asymptotic, a true asymptotic expansion. So it uses Arthur's work, endoscopy lift, and it also uses a weak while law. This is why on classical groups, so he considers the descent of the representation to one of the classical groups, and then he also has to, on the classical groups, he has to use a weak while law, and this is why he doesn't get a true asymptotic formula. But there's some ongoing work of a student of Frieden and trying to improve the method and trying to see if this gives really an asymptotic formula. Well, now let's see all of this, what I described here, except the results of Lindenstrauss and Venkatesh are based on the use of the trace formula. And now let me explain how the trace formula comes into play here. Well, the trace formula now of Arthur, this is a, so to speak, equality or identity of distributions on the Ardelic group. And the left-hand side, this is the spectral side, has an expansion in terms of distributions which come from Eisenstein series. And the geometric side has also an expansion. So these are, in principle, given in terms of orbital integrals. And, well, the main term on the spectral side, the main contribution on the spectral side, this is just the trace of the operator restricted to the discrete spectrum. So this is what we really want to understand. And the main term on the geometric side, this is just the volume times the corresponding test function evaluated at 1. And now the method is to choose appropriate test functions as I described it in the case of a surface. And for example, to study or estimate eigenvalues in some, like estimating eigenvalues in an interval or in a certain bounded set in A star. And well, the first problem you have to deal with is, well, you have to, so far the spectral side was not very suitable for these spectral problems because it's only conditionally convergent. And this is the first thing what you need, and it's a result of Finis, Lapid, and myself, which says that the spectral side is actually absolutely convergent. And now we have to understand the spectral side. And the distributions appearing in the spectral expansion, they generalize, so what we have seen, this kind of integral, which appears in the trace formula for the upper half-plane case. Well, it's quite complicated to describe the structure of the spectral side. But so the main ingredient is the following. We consider, so we start out with a parabolic subgroup. And so it has a Levy component M, and we consider the corresponding discrete subgroup. This should be M. I'm sorry, this is not G, it should be M. So we consider, oh no, I'm sorry, it's tried. So we consider the discrete subspace and the induced representation and the analytic or C infinity vectors in the induced representation. And then between induced representations, there's an intertwining operator, which is defined by meromorphic continuation. And well, we can also fix an automorphic representation on M, and then we get the isotypic subspace in the induced representation, and the intertwining operator commutes with this. So we consider we get the intertwining operator associated to every automorphic representation of M. And we also have the induced representation. This is the induced representation on this space, on the induced space. And and then a simple piece or part of the spectral side is an integral series like this. So if we have consider a maximal parabolic subgroup, then the main ingredient is, which replaces, so to speak, or which is the analog of the logarithmic derivative of the scattering matrix. This is logarithmic derivative of the intertwining operator, which enters here. And so now the important issue is, well, you have to deal, as I said, for congruence subgroups of SL to C, we know that the matrix coefficients are expressed in terms of the Dirichlet series. And so we have to see how to deal with this logarithmic derivative. And the first thing is what you get out of this theory. You can normalize the local intertwining operators and pull out a meromorphic function. And what you're left with is a product of finitely many local intertwining operators. And well, now this normalizing factor can be expressed in terms of L functions, and in particular, if we consider GLN and the standard maximal parabolic subgroup, then the normalizing factor has this form. It's given in terms of ranking, a quotient of ranking Silberg L functions. And now you can use, of course, all the known facts about ranking Silberg L functions. We know the functional equation. We can estimate the conductor and so on. And we know it's a meromorphic function of order 1, which is very important. And so, and we also have to deal with these local intertwining operators. Now, in general, well, if we want to show that all terms besides the main contribution on the spectral side are neglectable, then this comes down to the following two conditions. Well, the normalizing factor expressed in terms of L functions, we would need, so we need an estimation like this, which holds for all representations. So we fix some open compact subgroup. So we need this kind of estimation. Well, this can be proved in the GLN case because we use all the known properties of the ranking cybernetic L functions. And for the, as far as the local intertwining operators are concerned, we need to know that the poles, I mean, the local intertwining operators at finite places, the coefficients are rational functions in p to the minus s. And we have to make sure, or what we need is that the poles are uniformly bounded away from the imaginary axis, which, well, is a kind of weak Ramanujan estimation. Well, again, for GLN, this is known, yeah, it's a known fact, and again, Peter was involved in proving this. And so at least for GLN, we know that these two conditions are satisfied, and this gives essentially, at least on the spectral side, how one proves the while law in this for GLN. Okay, there are many more things to say about the while law, but let's now turn to another question, which is also related. Well, in a sense, it's related to the concept of harmonic families. This is limit multiplicity problem. So for the moment, we consider a connected linear semi-simple Lie group with a fixed Haar measure, and then the unitary dual equipped with the Fell topology, and the tempered dual. So then we know the discrete part decomposes decomposes in irreducible representations, and using the multiplicity, we make up this Borel measure on the unitary dual. So this is, well, this is a Borel measure, and then we are trying to understand, well, limit multiplicity means you want to study the following question. You consider, at the moment, let's consider any sequence of lattices in G. And then, well, you consider the corresponding, takes the corresponding measures, and you want to understand if these measures have a limiting behavior. So the precise statement is that this sequence of lattices satisfies the limiting multiplicity property if it, so if you take any bounded or Choran measurable set in the tempered dual, that the claim is, or then you want to know that the measure of this set with respect to the measures introduced in terms of the discrete group converges to the Plancherel measure of this set. And on the complementary, on the complement, it goes to 0. So a particular example is if you consider a discrete series representation, then it simply means if we normalize the multiplicity of the discrete series representation by the volume, then this converges to the formal degree, which is, of course, the Plancherel measure at this point. And, well, and this has been studied by many people, and it started with the work of George and Wallach. In these cases, you consider only a very special family of lattices, namely tower of normal subgroups. So you have a descending tower of normal subgroups of finite index intersecting in 1. And then the first work done in this context, this is due to George and Wallach, who, for example, well, all of this is in the co-compact case. And then they showed, for example, that limit multiplicity property holds for the discrete series. And the general case was proved by Delorme. He proved this in general for towers of co-compact subgroups. And well, quite recently they have been introduced a completely new method to study this problem in the co-compact case, which allows you to consider much more general families of lattices, not only towers. Now, as far as the non-compact case is concerned, well, there's preliminary work by Closel, who proved a weak version for discrete series. So he proved only that the limit, well, lim sub can be estimated by a positive number, and then, well, in general, the discrete series case of a discrete series representation was partially considered by Rolf and Spey, and the general case was treated by Savin. Now, currently, Finis, Lapid, and myself, we established at least that for the principal congruence subgroups in SLN, the limit multiplicity property holds. And now Finis and Lapid are working on an extension of this result to all congruence subgroups. Well, again, because this is based on the trace formula, application of the trace formula, and we need to reformulate this in the adelic setting. The adelic version is you consider an open compact subgroup in the group of finite adels, and then the corresponding measure is just the one which I have written down here. This is the measure which you consider, and then instead of, well, if the group would be simply connected, then this is one and the same thing. But in general, we would have, it comes down to consider a finite number of copies of locally symmetric spaces. So now you consider sequences of such open compact subgroups, and you ask exactly the same question: do the measures converge to the Plancherel measure? Well, this is the main ingredient. So you want to reduce this again to a problem about the trace formula. And the key ingredient is Sauvage-Shaw's density principle. This essentially means, so we consider here the space of test functions, smooth compactly supported functions on G of R, which are by K under the maximal compact subgroup, which are finite under left and right translations. And then we consider for such a function, we have can consider the Fourier transform, which is, well, so this is, so to speak, the Fourier transform which lives on the unitary dual. And, well, then if you insert the Fourier transform of such a function in your measure, then you just end up by, this is the discrete part of the spectral side of the trace formula normalized by the measure. And on the other hand, if you apply by the Plancherel formula, if you insert it in the Plancherel measure, then you get h, the value of h at 1. And now Sauvage-Shaw's result now tells us that in order to prove limit multiplicity property for these kind of lattices or discrete groups, you have to show that the measure at the Fourier transform converges to H1. And this breaks up the problem in two problems. Now you want to use the trace formula. On the spectral side, we have to show that if you take the spectral side of the trace formula, so H at the finite places, we just take the characteristic function of the of this open compact subgroup, subtract off the leading term, and then you want to show that this converges to 0 if n goes to infinity. But it's also equal to the geometric side, and here you want to show that this converges to the main term on the geometric side. Everything else in the limit disappears. And yeah, if you want to deal with this problem, you again face the problem that you have to understand all the terms appearing in the trace formula, which are not, so all terms which involve, so to speak, the constant, the intertwining logarithmic derivatives of intertwining operators. And now it can be also reduced as in the case of the while law, the two problems. One problem takes care of the normalizing factors, which you pull out of the intertwining operator. And now you have to have a slightly different behavior. So it has to have, you need a uniform estimate in the representations on M. And so you want to estimate these integrals. And so the level of the congruent, if this would be a congruent subgroup, this is the level of the congruent subgroup. Otherwise, it's, so to speak, the level of the largest congruent subgroup contained in here. And this is, well, it needs to be uniform in the infinitesimal character, and, well, this is the lowest k-type, or one of the lowest k-types, the Casimir eigenvalue of one of the lowest k-types of the induced representation. So this is one thing, and then as far as these local intertwining operators are concerned, now you have to, well, the coefficients are rational polynomials in pi to the minus s. And the main thing is to control the decrease of the numerators. Well, this is quite a subtle problem, but in principle, you have to be able to define these, to estimate these decrees again in terms of the level of the corresponding congruent subgroup. And now it's possible to show that for SLN, these two properties are satisfied. Well, currently, you might think that using the work of Arza or of Frieden, we can also deal with classical groups. At least it's conceivable that TWN is also true for classical groups, but it's in the process. There are quite a number of questions which have to be understood about the L functions occurring in this context. But, well, it's conceivable that it can be extended to classical groups. And, well, there's a lot more work in this context, which I haven't any time to talk about. This, for example, concerns the distribution of Hecke eigenvalues and so on. There's very interesting work, recent work by Shin in Template concerning the Sardo-Tate conjecture for a general reductive group, and there's recent work of Yasmin Matz about while law for Hecke operators on GLN. And there finally is also another very interesting development. This concerns, so to speak, analytic torsion, which is a more sophisticated spectral invariant. Well, so far we only considered, so to speak, eigenvalues in some given set in the unitary dual, but here you consider the whole spectrum, make out of this a complicated spectral invariant, and then you will also want to understand how the spectral invariant behaves if you move up in a tower, for example, or in a more general case. And this, surprisingly enough, gives you some information about the torsion in the cohomology of the underlying arithmetic group. Okay, but that's the end of the talk.
Thank you. Questions? Comments?
You said we are using functions of rapid decrease, but the functions of rapid decrease, clearly that's not Harishchandra's class. Is it something like the Kasselman-Wallach class? Or?
Yeah, essentially, yes. I mean, it's as I said, it's not Harishchandra class. But for example, a function like the heat kernel, this belongs to all spaces, Harishchandra spaces SQ, yes?
But we have something weaker
Yes.
Yeah.
More questions?
I think Steve Miller asked about this little annoying thing about this torsion. That you had.
Okay.
And is that really a serious problem?
Well, it's not easy. Well, of course, this is one thing you would like to rule out. You want, for example, to consider the full group, Bianchi group, anything like this. And this is related to the problem with the trace formula. Well, of course, the trace formula is valid for any discrete group. But to handle, for example, it basically arises, so you have to handle the orbital integrals. And the existing torsion makes this much more complicated. But of course, one expects without doubt that it works for all four groups with torsion as well, but it needs some work, yes.
Okay, so let's thank the speaker again, thank Werner again. So we continue in 10 minutes.